Dr. Carlos Hinojosa is a postdoctoral researcher at KAUST, specializing in computer vision, AI safety, privacy, and trustworthy systems. He has earned his Ph.D. with a Laureate distinction in 2022 and holds 2 US patents. He's recognized for his contribution at some of the top conferences like CVPR, ECCV, ICCV, and IEEE. He has also won the Best Paper Award at ICIP 22 for his work on privacy-preserving optics. So with that, please welcome me joining Dr. Carlos Hinojosa. Thank you.
Okay, hello everyone. I'm very happy to be here with you today. So yeah, today we are going to talk about AI agents in general, what are the capabilities this system has, and also we are going to talk about some safety considerations we need to consider before deploying them. So AI had advanced along 2 closely related goals. One is intelligence, which refers to the ability of this model to understand and reason about the world. And the other one is agency, which basically refers to the ability to act in the world and achieve some goals. So along these 2 dimensions, the 3 concepts have been raised. One is generative AI, AI workflows, and AI agents. So we are going to talk briefly about each of them. So generative AI are basically large foundational models that have been trained on billions of parameters using different types of data. So this model basically input one kind of data and output also multiple kind of data. But this model has some limitations. Well, like one limitation is that they have limited knowledge of proprietary information or external personal information. And also, these models are passive. That means that they wait for our prompt and then respond. On the other hand, AI workflows basically connect these models, these foundational models, to different tools through, for example, APIs, structured APIs. So in this case, for example, we have a model, a ChatGPT, Cloud, or any model that is connected to a tool, in this case a calendar, so we can ask a specific question about, or a specific question that use this tool. For example, what is my next meeting? When is my next meeting? But if we don't connect the right tools, then the model will be unable to answer some questions, right? So if we only have connected calendar, then we cannot ask about weather, for example. So in general, in AI workflow, you connect some tools, and then you define these tools, and then you ask the model to some specific question that will use these tools. So here is the main thing, is that for AI workflows, the human is the decision maker. So a human do the reasoning and planning and stack the workflow together to do a task. On the other hand, AI model, with that AI model, basically we want to replace the human with an LLM or a BLM. And the idea is that this model do the reasoning, the planning, and stack a workflow together. It designed its own workflow to do a task. And so they perform tasks based on their observations and context, and also they perform some decisions, but these decisions are isolated from other agents. So examples are like you can use an agent to check flights. You can use an agent to maybe get a flight itinerary and so on. So, sorry. So agent architecture this is like a general architecture for an agent, where at the center we have the LLM, an LLM core. This agent or this model, sorry, can observe the environment, and then it can plan and reason and plan some actions, and then it performs the action through using tools or maybe calling APIs. This model can also use their memory or context to reflect on previous interactions, and you can use also, and they also do monitoring or evaluation of these results or the feedback to adjust their behavior. So this is a concrete example of an agentic system, called OS agent, operating system agents. This agent has, we can categorize these agents on two types. One is agents with tools, and the other one is agent with primitive controls. So with agents with tools are basically OS agents that interact with different environments. For example, email environment, calendar environment, online shopping, etc., using only API, through API calls. On the other hand, we have agents with primitive controls that basically, these agents operate like a human do. Like they use, they observe the screenshot, the terminal, the accessibility trees, even they can access to the Microsoft camera, etc., and they can use low-level controls like keyboard, mouse, and system-level APIs to perform actions. So as an example of observation space, so we have observation space and action space for the OS agent. In the observation space, we have a screenshot with UI annotations, and also we have accessibility trees. So this is the tools, or this is the things that the agent observes, and then it performs some actions based on low-level actions like using the keyboard, using the keyboard API or a low-level API, and also the mouse. And they also incorporate some states, like they store some variables, environmental variables, and also some instructions and reasoning. So this is an example of an OS agent in action. Basically, we use cloud here to organize the desktop. It do the reasoning, then they perform some actions, and then eventually they organize the desktop using their mouse and keyboard. So AI agents, well, although these agents can operate independently, they have some limitations. So first limitation is that these agents rely on multiple external tools to extend their capabilities, which introduce inefficiency due to limit integration and require also additional configuration. On the other hand, agents has limit memory or context window, so this model, there is a restriction on the amount of information they can process, and also make it difficult to retain and use long-term information. There is also another limitation, is that these agents can handle multiple tasks, but they lack of specialization. So they rely on general decision patterns, but they don't have fully expertise on a specific task. And finally, they have limited reasoning capabilities when handling multi-step or ambiguous problems that require deeper contextual understanding. So now, multi-agent systems are basically, or are systems that consist of multiple agents working together to perform a task on behalf of a user or a system. So we have here an example where we see a multi-agent system for video processing. So we have a central agent. We have an agent specialized on analysis. Also we have an agent that creates on assets, and so on. So each of these agents has expertise on a specific task, and they collaborate together to perform different tasks on this multi-agent system. So this makes the system more accurate because each of the agents can cross-check their information. There is more adaptability because these agents adjust their output or their strategies based on the feedback received from other agents. And also, they have more scalability because in this system, as you can see, you distribute the workload of the task. You distribute the task among different agents, which make it easier to handle larger and more complex tasks. So this is an example of a multi-agent system platform that is called Eigent. This is a startup from a KAUST alumnus, and it was built on top of Camel AI, that is open source. So basically, you can see that you have different agents, and the task here is to create 200 video games, and you can see that they create the video games in parallel. So this is because the system redistribute the task among these agents, which make it more or very efficient to perform this task. Okay, so in a multi-agent system, the information flow between the agents, and the way this information flow define the architecture. So we have centralized, decentralized, and hybrid architecture. For the centralized architecture is basically that we have a central authority or an agent that collects all the information reported by the other agents, and this agent collects that information, processes the information, and also redistributes information among the other agents. One issue with this approach is that if the central agent or the central authority fails, then the information or the other agent lose access to the information or critical information provided by the central authority. There is also the decentralized approach where the agents collaborate between them and they share the information between them. But without a central authority, this interaction could cause misalignment because each of the agents interact and do actions differently depending on the received information. And finally, we have the hybrid approach where we combine both of them. So we have a central authority, but also we have some freedom between the agents to interact between them. So, a system is defined by how agents make decisions together. So we have systems that, for example, do cooperate. So we have different agents that cooperate towards a shared goal. Or we have some system that performs some competition between the agents. So in this case, each agent optimizes its own goal and also adjusts their behavior according to the behavior of the other agents. And also we have a mixed approach. We can also see different structural categories like hierarchical, where we organize the agents according to different levels of controls. Then we have the heterogeneous approach, where each agent has a specific role and they interact together. And finally, mixture of experts means that we have an authority that redistributes the task to a specific agent depending on the expertise of each agent. Okay, so of course this brings some challenges. So if we have a system with a lot of agents, then we need to care about these challenges. So the first one is that in this kind of system, if one agent fails, then the failure propagates this error to other agents. Also, if one agent behaves adversarially, then this, or is jailbroken, then this failure is also propagated to the other agents. Then we have the coordination complexity, that is as the number of agents grows, the coordination decision and decision becomes increasingly difficult. And finally, if we have agent that, the agent dynamically adapts to the environment and the other agents, so because of this adaptability and this interaction could lead to unpredictable system behaviors, is one of these agent fails. Okay, so so far we have seen that multi-agent system can be extremely powerful, but with this power also come a lot of risk, right? So at high level, this risk can be grouped in these three types of misalignment. So we have user misalignment, that is when the user intentionally requests a harmful or unsafe action to the model. We have also, we call this misalignment because the user goals don't align with the system safety constraints. Also, we have model misalignment, that is when an agent misunderstands the goals, constraint, or context. And we finally have the environmental or environment misalignment, that is when external system, website, files, or tools behave adversarially, and also they hide some hidden, they have some hidden intents. So this is an example of kind of recent paper where they do a benchmark across these three types of misalignment we just discussed. So, they define these three categories. The first one is deliberate user misuse. This is similar to the user misalignment. Then they have also prompt injection attack, that is an example of an environmental misalignment. And we have also model misbehavior, which is the corresponding to the model misalignment. So they evaluate these models against different tasks, real operating system tasks, which use, for example, Visual Studio Code, Chrome, Google Chrome, Gym, etc. And as you can see from the numbers, basically the trend is that this model has common unsafe behaviors. Okay, so this is an example of a prompt injection attack. So basically here we have a website, or the attacker designed a website, and you can see that there is a GitHub issue where basically the title of the issue is kind of a prompt, and this looks benign because you basically wants to or needs to combine some string to solve a problem, and inside the answers there is the attack. That is the attacker basically include a way how to solve this issue, and in that response the attacker include the website. And the website is basically could be, for example, a website where you input every input you do, like text input. This input is sent directly to the attacker's database. So this is how it looks. So basically, you ask the model to please investigate this issue in GitHub, and the OS agent go to the issue, and then it start navigating the web page. It scroll, it sees some details, and also start clicking So it clicks the website, and then at some point, the model copy information from your profiles or website profiles directly into the attacker's website. This happens because the OS agent has access to your computer. It's like you using your computer. So you have, for example, pages. I don't know, for example, booking. You have booking open, and you have already logged into the booking. So the agent can copy information and paste anywhere. And in principle, you can see that this could look benign because you are basically just asking the model to investigate this issue. But it has some hidden intention. And this is an example of prompt injection or model or environment misalignment. This is just an example, but there could be more. So solving the prompt injection problem at the LLM layer is very challenging. And this is very similar to a problem we have in computer vision, where we have a system, a classifier that correctly classifies cats. But when you include or you add some adversarial noise to this cat, then the model, the classifier doesn't perform really well. This is very, very similar, and here is another example of how to attack OS agent. So we have a prompt that is basically go to the social media, for example, go to Blue Sky, and then summarize the content, and the agent go. But when the agent get into the web page, it see an image, and that image contains an adversarial patch that is not visible for us, for humans, but internally, that patch makes the agent to perform different actions. So for example, repost or go to another website that is not the intention of the user. Okay, so one key lesson from recent work is that defenses at the AI model level are brittle. So in agentic system, specifically when we use multiple agents or even one agent, the safety must be enforced at the system level. So we need to design guardrails. For example, here we have sandboxing. This is an example of guardrail where we give. In this example, we can see that we give the model a prompt. The prompt basically asks the model to retrieve some information, including the email from a person. And so we have the privileged LLM that basically do all the reasoning, the planning, and also generate a code. But when we want to process sensitive data, in this case the email, for example, retrieving the email, in this case, we rely on a separate environment or separate LLM that perform this email retrieval using or following some policies, security policies. And this environment is separate and is protected against any, maybe against actions or action that this agent could perform. So this is effective in structured tool calling scenarios, but how can we implement this, for example, for vision agents, like we saw before? This is an open question, and people is working on that. And also, of course, when we increase the number of agents in multi-agent system, this increases the complexity and therefore increase also the safety risk. So I borrowed this interpretation from Professor Florian in his previous talk in a workshop in ICCV. So I share yeah, his interpretation that is current agents are a bit like minions, right? Because they are not completely reliable, but they are very powerful in some domains. They are very skillful and powerful in some domains. Although they do what they are told, even if that's evil, and when they work together and coordinate, they become very, very efficient. However, it is much easier to use these agents to, oops, what happened? Okay. So we can use this, we use these agents to, or it's easier to use these for bad than for good. So we need to design guardrails for them or design protocols for safety, like, for example, the sandboxing approach, certification, and so on. And AI security is no longer an academic or exploratory topic, because here we are deploying AI agents in real products with real security risks, and it's being used by millions of users. So as a result, the security evaluation must become more rigorous, not less. And finally, the current AI may cause many new forms of harm. So their reasoning is very good, but they limit, or because they are not completely reliable, this limit the suitability for using these systems on different applications. Okay, so that's it. Thank you very much for your attention.